DeepViz. Explaining long short-term memory network with high-dimensional time series data. Neural networks are used for solving many problems effectively, including stock prediction, self-driving cars, handwriting recognition, medical image analysis. However, the deep neural network is still a black box, leading to difficulty in understanding and explaining why a model works or fails. We introduce a way to open the black box with long short-term memory network, also known as LSTM network. Here is a typical structure of an LSTM artificial neural network, contains LSTM layers and dense layers of different sizes and configurations. We will explore what happens to the network components. In particular, we try to depict and explain the mathematical model of neural net. On the left is the structure of an input or intermediate node, and on the right is an output node. Instances are listed vertically, cell colors encode the temporal values of the series. We reorder the data entries based on their values in output when visualizing the heatmap of the LSTM layer and the scatterplot of the dense layer. This ordering is intended to help people recognize some of the patterns included in the result. The ordering of instances is for visualization and does not impact learning process. Demonstration on real-world datasets. Here is the interface of DeepViz. Users can select input data from Load Model button and then start. Users can play around with input data from High Performance Computer Center, SP500 stock data, or US employment data. Here we start with High Performance Computer Center data. Users can also save the trained model to local storage. For model configuration, user can modify the hyperparameters of the model, such as epoch, batch, and learning rate. Training and testing loss are visualized with mean square error measurement and can be traced back to see history of training with evolution of weights. For a typical model of LSTM network, input gate, forget gate, cell state and output gate are specified. Weights can be filtered for a clearer visualization. The hidden layers can be added or removed. For this high-performance computer center dataset, as you can see from three first layers. The first layer is input, and there is no pattern. The second layer shows somewhat a pattern for input. The third layer presents more clearly the temporal dependency as we can observe a diagonal pattern. For SP500 stock data, we trace back at epoch 10. The history of weights shows a shift in both magnitude and sign, positive-negative, of this set of parameters. The originally thick lines decrease their width, the originally thin positive lines switch into negative and adjust to the larger magnitude. At epoch 3, the scatterplots for training MSE and testing MSE both contain a vertical formation of outputs. Negative input will result in zero output in ReLU function. In the early stage, the learning process just started and parameters are not tuned properly. Moving on to the US employment data. We can see the contributions of significant variables to the output. The first node contribute with greatest positive contributions, opposite to the second node. While the other two nodes make marginal contribute as the observed links are really thin. These two last nodes do not demonstrate any clear patterns to learn. Thank you for watching.